Okay, let's go ahead and get started. Again, I'm Michael McClellan with L3 Levine Electronics and Electrics, and welcome to another webinar. A few housekeeping items. This is a webcast format, so all of the attendees' microphones are muted. This eliminates the problems we've had in the past with dogs barking, exterminators chatting, and wives chatting. So we are very happy today to have you on our webinar. To the right, you'll see a few buttons, and we would love for you to interact with us. There is a question button where you can ask our presenter questions. And there is also a handout. You can download a copy of Chris's presentation for future reference. Chris has been with L3 a few years now, and previously worked at Semenco, where he designed and built custom engineered variable frequency drives. So we're very lucky to have Chris today. He has a very in-depth knowledge of the product. And without further ado, I'm going to turn it over to Chris Vance.
Thank you, Michael. And hello, everyone. Thanks for coming to the presentation. My name is Chris Vance, and I'm with L3 out of the South Florida office. And today I'm going to be doing a presentation, the basic troubleshooting for the Danfoss VLT series drives. And as he said, there's if any questions, if you'll fill in the question box, we'll get to them as best we can. And without any further ado, let's get going on this. Let's see if I can get everything to operate. Okay. So the VLT series drives for Danfoss are shown in this picture here. We do have soft starts, which I won't be addressing today, but Danfoss makes the drives, VLT series drives, through the micro drives all the way up through, up to 1,000 horsepower in very different configurations. So today we're just going to do some basic troubleshooting that the layperson can perform in the field to try to help get a problem with the drive resolved. My experience is most of the problems that we have with drives is very simple one. So that's kind of the approach we're going to take today, is just some basic troubleshooting guidelines. And I'm going to be referring to the user manual, which comes with the drive, application manuals, which are on the Danfoss website, a service manual, which if some of you out there are familiar with Danfoss and you've gone to their service schools, you might have some of these manuals, or we can make some of that available to you. So that's where most of this presentation is going to come from. And I'm just going to go through this briefly here on going after the drive on a powered down state, just to go check everything on the drive. So in this presentation here, we're going to do everything without power applied. Always ensure everyone's safety by verifying that the input power is tagged out, locked out, and no voltage is present on the drive. Some tools, some basic tools, standard screwdrivers, Phillips, flatheads. The Torx drivers is the only thing that would be non-common, maybe in a lot of people's toolboxes that you would have. And the Torx drivers, they are used to take on and off the covers mainly, but they are used extensively in the VLT series drives. Metric sockets, long extension, torque wrench, that type of stuff. Some equipment that would be useful if you had. The voltmeter, PWM compatible voltmeter, that's the only one that's really required for this basic troubleshooting. Clamp on ammeter is always useful as well in the field, and that's more when the drive is in a running state or you're powered up doing some power checks. The reason we say a PWM compatible meter is the drive itself, when it is powered up, it generates a PWM signal, which sometimes gives erroneous readings. If you don't have a meter that's capable of reading this PWM type waveform, so it could give you some false readings, and it's pretty standard today with the most new meters that they all are. But I just wanted to make you guys aware of that. Some other possible useful tools. Danfoss has software called MCT10 that you can check parameters, you can check setups, you can do some trending on there if the drive is running. A megger for the motor if you suspect motor problems, and of course the oscilloscope. And again, these are for when the units are powered up. And the other useful, powerful tool is the 1-800 or 188 Danfoss number. Tech support is very good getting things resolved for you, and they're available 24/7, free of charge, to answer your questions. So how I started out was troubleshooting mostly is something very simple, something that's overlooked. A miswire, a loose wire, something not being physically right. So we're just going to take an approach here that let's the logical, just eliminate things one by one to make sure that everything is right before we start saying the drive is faulty and wanting to replace things. We're going to take a look. We're going to assess the situation. We're going to do a physical inspection of the drive, narrow down to one of these sections that we think is possibly causing the problem, and then we're going to zero in on that and see if we can correct that. So these are the first things we're going to do. Is the unit installed correctly? Are the connections tight? Is the environmental conditions okay? Being installed correctly, the Danfoss VLT series drives come in many options for enclosures, from open chassis all the way through NEMA 1, NEMA 12, NEMA 3R, NEMA 4. So we're going to say, is this installed in the right environment with the right enclosure? Connections can be control connections, power connections, grounding connections, and such as that. So that's what we're going to touch on first, the obvious. This is from the manual. All the manuals that you have will give how the unit should be mounted. And this is showing that side-by-side mounting is allowable on the Danfoss series drive. However, you have to have a minimum space above and below the VFD for proper airflow. Obviously, if that's compromised or reduced, you could have overheating issues causing problems. The other situation here on the right-hand side is like our NEMA 4 products. Our NEMA 4 products are commonly mounted on pumps outdoors where they're trying to put the VFD close to the pump, and they're mounted outdoors, so it's NEMA 4, NEMA 4X. And these are mounted typically on some unistrut. Well, when it's mounted on the unistrut, we need to add a back plate. The back plate is going to ensure that you have proper cooling. So if it's not, the drive unit is not mounted to a wall, if it's mounted to a unistrut or something that doesn't have continuous coverage on the back, we sell the back plates that channel the air so the cooling is proper. So Do you have the required airflow above and below? And is the unit mounted properly with a back plate? Simple stuff, but sometimes it gets overlooked and can cause problems. It might not cause a problem right away. The not enough air and airflow, it could shorten the life of your drive because you're running it in a much higher environment than environmental temperature than it's designed for. So it could cause problems down the road. Also in the manual is how to access the control and power wiring in the drive. So the top picture with the small screwdriver, you can pry open, there's a little plastic cover to access the control board. Some people like to not use that method and remove the keypad, and then you can just use your finger to snap down this little tab that's inside here and take the cover off. And that's the access to the control cards. To access the control cards and the power terminals on our NEMA 12 and NEMA 4X drives, you'll need the Torx screwdriver to remove the cover to access it. And you'll notice if you install the VFDs, if this is a new install, that the Danfoss provides mounting glands, mounting hardware, and they're very specific on how the wiring should be done to eliminate noise issues within the drive itself. So you see here the motor connection. Danfoss recommends shielded cable for your motor connections. And what this is showing here is that shielded cable with no pigtails, what you'll do is you'll cut back a small strip of the plastic jacket and expose the shielding. And this is supplied with the drive. It's a metal bonding, so it provides 360-degree bonding on that shield for the motor to help with noise and interference. On the input side, you notice all the grounds, very short, very close. The ground for the motor, the ground for the incoming supply. Our smaller units, I think 20 horse or 30 horse, I'm not positive on that. They all come with removable power terminal connections, which is nice, very convenient and easy to use. Also, if there is a problem with the drive to remove it, you can simply remove these terminal blocks, swap out the drive, put a new one in, and be back up and running very quickly. But this is how the wiring should be done. It's very short, no loops, and your grounding wires as well, very short. This is some of the cable that you would see. It's in the field. It's on the marketplace with a shield, and this goes through typical types of wire, and whether it's multi-conductor conductor cable or single conductor cable. And then this just goes through some points of the type of earth connection and the size of the grounding connection, and so on. The motor screen here, the last portion of this, the motor cable screen must be properly terminated at both the VFD and the motor ends. Again, they would like not to see pigtails on the motor end. They recommend the EMC cable glands to be used on the motor side, but those are some of that are recommended. Now, I have been in the field on startups where shielded wire is not used. It is not required, but it's a recommended best practice to use shielded for both your power and your control wires. So these are some of the examples of the wire that's on the market. And here are 4 drives next to each other, where the first drive that was installed looks like the cable was, the screen was connected and properly terminated. Ground wire is coming straight in, very short, proper size. However, the next 3, someone forgot to install the shield cable on them. Could cause problems with radiated noise or noise that might affect other equipment in the facility. So you'll want to look at that if that is causing issues. Is look at your power wiring. Your motor on the motor side is RFI is radiated from the motor cables. So that's going to be any RFI energy is going to be going out and exposing other equipment to that noise that's generated there. And RFI is conducted on the mains. So if there's other machinery that's causing noise in the facility or inside the enclosure, it's going to be conducted through the ground plane up through the mains. So that's why Danfoss is very concerned about this and wants to do best practices. So on the same as the power cables, the control terminals, we basically have 4 connectors on the control card. Connector 1, the large connector, that's all your I/O. That's all, would be all your start, stops, reset, that type of stuff, 24-volt control. Your number 2 connector is your serial communications on the smaller drive, which is the Danfoss, which is the Modbus 485, which comes standard on all the drives. And then 3 would be for your analog I/O, analog inputs and outputs. Connector 4 is where is a serial connection for your laptop, where you would hook up the MCT10 software for commissioning a drive and or storing parameters, changing parameters and such. This is serial communication connection, which would be your Profibus, DeviceNet, things along that line, something that's other than the 485 Modbus that's comes standard with a drive. When the serial option is chosen, this is the connection point on the top of the drive, on the top of the keypad. The actual communication card fits below the operator, and you'll notice that it comes with what they call a decoupling plate. So once again, shielded cable. The 2 wires are very short and direct, and this cable has skinned back, and you depress, there's a little spring on the back side, so you push that up, feed your cable through it, and you release it, and now you have another 360-degree bonding for noise. And that's a properly terminated serial communication option board connection. You see here Pigtails. You'll see this throughout the presentation. Pigtails is not something that is good. It actually acts more like an antenna sometimes. So this is the preferred method on all the VLT series drives. As well as the control wiring, the grounding and bonding plate is here, this whole metal that is ground. And each wire is going, here's your analog wires, your digital I/O, your serial communication 485. Each wire is stripped back with the shield in between these 2 grounding points or bonding points. Again, you'll depress the spring, insert your cable and release the spring, and now you have again that 360-degree bonding. for your control input. And all of that is just to ensure that there's no EMI, RFI, or any noise issues, erroneous signals that's causing the drive to misbehave, or your drive is causing something else to misbehave at your facility. So again, this is just touching base, kind of putting everything in one page of what I had just talked about. Screen signal cables. Make sure the bonding is bonded correctly and is with the approved 360-degree plate that's provided by Danfoss inside the drive. Avoid creating loops with pigtails. Keep everything tied down and as short, as straight as possible. And you should be good with any noise issues. Oh, losing my, there we go. And grounding, are bonding. They're both used interchangeably in the Danfoss manuals and such. So what we're talking about here is the grounding and the VFD installation. Is a ground cable between the panels. You want to ensure a low impedance, so as short as possible connector. You also want to provide stranded cables or braids. They provide a better conductivity. If you have these bonding straps, that would be better. But just to make sure that the bonding wire is large enough, sufficient enough to have low impedance and be as short as possible. When you are mounting the VFDs to the panel, it's good practice to use star washers so that the paint that the actual drive is mounted to, you have a good surface to ground. And usually that's achieved when you, if it's not a galvanized type back plate, if when you're installing the drive, you use a star washer to mount the VFD so that it cuts into the paint and you have a good connection between the drive and the back panel. And the standard practices of separation of control and power wires. Use separate conduit entrances for power wires. If your power wires do need to cross your control wires, make sure they cross at 90-degree angles to eliminate any noise. And here's just an example of what Danfoss would not recommend, is having your ground cable, this long cable going from the drive all the way down to the bottom of the drive. Very long, and actually has a lot more impedance than if you drop the ground right next to the drive or had the drive properly grounded through the back panel. So that's just one example of what they would recommend not doing. And if there is problems with false tripping or noise, that could be an issue. So we've gone through your basic, put your eyeballs on it, make sure everything's tight, make sure everything looks good, the wiring looks good, it's nice and neat, properly terminated. So now we're going to look into the drive. We're going to start looking for blown fuses. Obviously, if there's carbon deposits inside, that's not going to be a good day for the drive. But we're looking, and we're going to do some static test where we're going to use a multimeter to try to get inside the drive and actually measure the power components within the drive to make sure that nothing internally is damaged. So we're going to try to address determining whether the diode bridge is bad or faulty, or your IGBT devices are faulty, and that's what we're going to go through in this section. So the drive, the input to the drive is composed of input diodes. So what we're going to do, we're going to have the multimeter, and we're going to set it in the diode measuring mode. And what the meter will do is, depending on the polarity that you put across the diode, cathode or anode, one is going to be forward biased, so you'll get a voltage drop. In other words, a diode will conduct and pass current. And if you reverse your leads in the other direction, it will not pass the current and it should be open. That's the proper resistance or measurement of a diode. And these are just some typical values that you would read. And I have analog meter in here as well. Some people still like the analog meters, which doesn't have the diode mode. And again, you'll see a forward biased with the terminal. You'll have your positive lead on the L1 terminal and your negative lead on the positive bus, and that would forward bias these diodes. So those are some of the values that you would expect to see on a healthy diode. In order to check a diode per that previous chart, you have to access the power inputs and power outputs, which would be here. And then depending on what size drive you have, this is a small A-frame size drive. This is a very small 5 horsepower, 3 horsepower size drive. You'll see that the plus and minus bus is right here. And your UVW is here, and L1, L2, L3 is here. So that is your bus and your power terminals. On the larger drives, your AC input and your output. And your DC bus link is located up here. They're actually test points. So you'll have to refer to the manual, and depending on the size of the drive, the DC bus test points are located in different areas. And what we're going to do is we're going to take our meter, set it on the diode scale, and we're going to connect the positive lead to this positive DC bus terminal, and the negative lead we're going to touch on L3. Okay, and we're going to do L3, L2, and L1. In this particular arrangement, they should be all not biased on. They should be in the open or capacitor charging effect. So this is going to be the OL, or the 0, that you're going to read. Now, if we reverse the leads and put the positive on the L3 and the negative on the positive bus, where the meter now should be forward biased, and you would read between 0.3 and 0.7 volts, typically about 0.5 volts, somewhere in between there. With those readings, you have just checked L3, L2, L1, you reversed your leads and did L3, L2, L1. If they all pass this test, then your diode bridge or your front end is okay. There's nothing faulty about that. There's no damage in the diode bridge front end. What you would expect to see is a short. So in any of these modes, if you saw something other than open or 0.5 volts, that there's a problem. So far we've come through this, and let's assume that we've gone through and all of these have matched. So we have the diode bridge has been confirmed that it's okay. The output transistor check is basically the same way. goes through the same type of readings, and here's the typical readings that you would see depending on where your positive and negative lead of your meter is placed. Is you actually on the output of a drive, the IGBTs, they have a freewheeling diode across the collector and emitter of transistors. So you're actually reading through that diode, and that's typically what fails when a transistor goes bad. So you're doing the same arrangement you did on the front, is you're taking your leads from UV and W, and the other lead of your meter to the positive and negative side of the bus. And you should get 0.3 volts to 7 volts in one direction and open in the other direction if everything's fine on that. And the other test that I like to do, remember the power is off, so there should be not connected to any transformers or anything up here. So I check the inputs, check input and your output shorts. So I do line to ground on both input on the motor and the input side. This would check sometimes in conduit, you'll get a nick or something on a wire, or in a junction box on a motor, you might get something going on there. So you can check from line to ground and line to line shorts on the motor. Now, if your motor's connected, you're obviously going to read through that motor, so you will see some resistance. It should be a low resistance, but it should be some. If you do get some weird readings on that, go ahead and disconnect the motor from the VFD itself. You can check for line-to-line shorts on the VFD side, and then you can check your motor connections. If you happen to have a Megger test at that time, this would be a good time with the motor disconnected for you to go ahead and you can check, you can meg the motor and verify everything is fine with the motor itself. Okay, so what we just did is we went through and we verified that our input diode section is good, our output IGBT section is good, and our line to line and line to ground, we're all good on that side. So now let's just talk a little bit about what's internal to the drive itself on the power side, and talk a little bit about the design and some things that we can arrive at if a problem is being caused, and what device we might want to delve into looking into closer. A VFD is a fairly simple animal. It's made up of a rectifier system, or a system that takes an AC sine wave, converts it to a DC level, which would be your diodes. It stores it in what they call a DC link section, which is basically the power bank of the drive. And the output section is the inverter. So it inverts back to AC. Chops up this DC and makes what they call a pulse width modulated output. And then of course you have your control and regulation, your control board, your firing boards, your power boards, power supplies, and control keypad that make up a drive. And this is what the actual drive internal looks like. We'll go from the input all the way to the output real quick. On the input side, we have Danfoss has MOVs and a Zener diode arrangement. It's a pretty unique design that they have, but it's for surge protection on the drive. The next is RFI filters. You cannot buy a Danfoss drive without an RFI filter in it. Some other manufacturers, you buy that as an external device, but in the Danfoss world, you get an RFI filter with your drive. And there are many different types of RFI filters to choose from, but you have to have a filter in the drive, which goes back to their philosophy on the proper wiring and such that they think it's important for proper operation and longevity of the product to have this. Then we go into the rectifier section, which is the diode bridge. And then we go into the DC link portion, which is it smooths out the ripple that's in this DC supply, which is an inductor and capacitor. We have the 6 IGBTs on the output side, and we have CTs, current transformers, so we can monitor overloads, overcurrents, over torque, that type of stuff on the output. And then we have the motor, and that's the simple block diagram of your VFD. Now we'll go into exactly the layout of the VLT series on the different sizes. The rectifier section, as I said, is to change AC voltage into DC voltage, and Danfoss employs 2 types of rectifier sections. The smaller units, they use what they call an uncontrolled rectifier section, a diode bridge, what I've been showing in all the drawings thus far. On the larger units, they have a controlled rectifier section, which is an SCR or thyristor and diode bridge. So the first we're going to go over is on the smaller units, is the diode bridge. AC comes in, it directly converts to DC voltage on the output. And it has a small ripple in there. We'll talk about that a little bit in a few slides. The second type is half diode and half SCR. So what this will do is it will slowly, instead of instantly from AC to DC, it slowly phases on this side of the bridge and slowly charges up your DC bus voltage. Okay. And on the input side, I mentioned the MOVs, an MOV and a Zener diode. Danfoss drives are compliant with code. It's called the VDE 160. And what it is this certifies that the drive will withstand 2.3 times the line voltage for 1.5 milliseconds. So this is a rating that's, as you can see, is allows for our drives to be much more tolerant of spikes, voltage spikes, and protection. And it employs a MOV, a metal oxide varistor, as well as a Zener diode arrangement. So on a typical 480 volt application, the drives can withstand, without failure, a spike of 1,104 volts. That's pretty robust design. On the 240 volt, you can go as high as 559 without any damage to the drive itself. The next section is the DC link section, and this is used to filter and store your DC voltage. Like I said, it's kind of the power bank of the unit. A lot of times, if you're talking to tech support, they'll refer to the DC bus voltage a lot. They will want to know what the voltage is and maybe ask you to look inside the keypad for that. And it's basically comprised of the DC link inductors, which we showed you, soft charge circuitry, DC capacitors, and the braking circuitry, which is optional in most cases. So the soft charge circuit, when you apply a DC voltage directly to a capacitor, it looks like a dead short. So what you have to do is you have to slowly charge that capacitor up, or you'll get a tremendous inrush current, right? So what we have to do in between that diode section, when you're changing AC to DC and putting it into these capacitor banks, we want a soft charge, or we want to slowly increase that voltage until they get fully charged and there's not the inrush. So on our drives, again, depending on the size, we would use a contactor with a resistor circuit, or we would use the SCR Diode Bridge circuits for charging. On the smaller drive, what happens? Your AC voltage will come in, it's converted to DC, it goes through the smoothing inductors, and then it's going to go through this resistor. And this resistor and capacitor form an RC network. So you're going to charge up, it's going to slowly charge up. Your power board is monitoring the DC bus level, obviously. And once the DC bus level is charged to a sufficient level, it will send a signal to this contactor to close, taking that resistor out of the circuit. Okay. This is the only moving part besides a fan in the VFD. So what would happen if this coil burnt out on this drive and you tried to run the motor? Well, this would remain open. The power board tells it, hey, close. It sends a voltage to the coil, but the coil is burnt. And so you press run, and now you're going to pull all your current through this resistor, and it's going to burn up. So that could be a possible failure mode, to where you are a scenario where you have your input voltage. It says, I got my input voltage, but everything's dead, you know, on the card side, or my DC bus voltage is not up. So that would be an obvious problem, would be your pre-charge contactor. This is in all the smaller units. I think through, I want to say 15 horsepower. So in the larger units, what they do is they use the SCRs to eliminate this pre-charge resistor and contactor. And they simply have another firing card over here to produce the firing angle of the SCR. And we slowly charge that capacitor up via the SCRs. And there is the in-depth on this SCR diode arrangement is when the AC is applied, and this is not phased on, there's no voltage getting to the power card or the control card, so there's no power. Your keypad won't turn on. You can't do anything. So what they have is a very small circuit, a very small miniature diode bridge with a limiting resistor that when AC is applied, these will turn on to conduct and have DC, and you will slowly charge or have power to power up your card, your control card, and all that. Then when you press the run button, this will turn on the SCRs and phase them on. So this is their power supply. In the past, what they would have is this would have been connected to a transformer. You would connect two lines of this to a transformer, a step-down transformer, which would drop your voltage down to control voltage levels, and you'd have a switch mode power supply on board. With the VLT, they've got rid of that circuitry, and they use this type of arrangement in their SCR diode bridge arrangement. But next, we talked about in this section is DC inductors, or DC chokes, as they're referred to. This is in there, and it helps with power line harmonics. A DC link choke in the VLT drive, as you saw, is both in the positive and negative legs of the DC bus. Without a DC link choke in your VFD, most people would install an input reactor to help with eliminate harmonics. On the on the line. And what the VLT series drive does is this DC link choke, which is internal and comes with the drive, is equivalent to about a 5% input reactor. So if there is a VFD, if you're using a VFD and it does not have a DC link choke, a lot of times you'll have to install an external three-phase reactor on the input size. You're basically at let's see, on your diode without a DC link choke, your total harmonics is up around 80%, somewhere in there, 70 to 80%. By installing a DC link choke or a AC reactor, you drop it down to about 40%, 42, 43%, somewhere in there. The advantage of the DC link is obviously it's not an extra money, it's not extra space on the panel, and it actually has an advantage over the AC reactor that you would install. If you think about it and you install a 3% line reactor, what you're doing is you're dropping the voltage that is available to the motor by 3%. So sometimes I've heard it say that, you know, input and output reactors are like chicken soup. It can't hurt anything. Well, in this type of design here, you have a 3% drop on the input side. You have your DC link. If you're using a VLT drive, that's another 3%, 3 to 5%. And you have the same drop on the output side. So you're having a total of 9% voltage drop on your motor. Reduced voltage on your motor increases current, which increases the heat. But it also reduces the available torque that you have. So you could get into trouble by applying too much of reactors and input and output reactors is my whole point here. But the VLT, the internal DC link chokes is equivalent to a 5% input reactor. Now, there is another use for input reactors. If you have large swells or sags in your voltage, or you have dirty power, it's very unclean, an input reactor is used for that. It's not to address harmonics in that case. It's used to address the poor power quality that you have. If you can imagine, if you have spikes on your line from whatever, if you have large DC equipment or heating equipment, that type of stuff in your facility, you can get line notching and spikes and all that. And what that does is that wears and tears on your input diode bridge or SCR section of the drive there. So input reactors used for that type of protection, that's another story. But for harmonics, the DC link choke is actually the best solution there. And then we have the DC bus capacitor banks. These are DC capacitors that are in parallel series. And your DC bus voltage, just for reference, I usually use the square root of 2, but the actual number is your DC bus should be about 1.35 times the input. And that should be roughly where your DC bus is. And again, that's another measurement tool that you can say, well, my voltage is this, but my bus is this. And if they don't match that conversion factor, then there might be an internal problem with one of these components. So that is your DC bus section. And a DC bus is where you would get trips on under voltage and over voltage type trips. We're going to talk about in this section when you get over voltage trips and what can be done about that. When an inverter is operating normally, the current is flowing from the input out of the transistors to the motor. And when you have an overhauling load, which would be some type of elliptical press, a downhill conveyor, or if you're having to stop a motor in half a second, it has a lot of inertia. What happens is your motor turns into a generator and starts to push voltage back through these diodes and starts to charge up your DC bus. Well, your DC bus has to be protected. It can only go up to a certain voltage before it will be damaged. So your unit will trip out on overvoltage. So if your process is, like I said, some type of overhauling load, a downhill conveyor, or you have a high inertia load that you need to stop very, very quickly, what they will do is we will add a switch, which is basically a transistor across the DC bus, and we will connect a resistor. And so all that energy from the motor is now shunted through the transistor out to the resistor and is dissipated as heat. And this is the output section with the brake IGBT. And again, that's the smaller units that will come as standard. The larger units, you have to order it with the brake module in it. The smaller units are usually the diode, brake chopper, and IGBTs are all in one block. They're not separate like they are in the drawing. They're all one power block. But this is the brake circuit, and you would have to size the brake resistors accordingly to the duty cycle, which we could help you out with that, figuring out the duty cycle and size of the resistor and so on and so forth. All right, looks like we're a little bit behind on time here. And finally, the output section is current transducers. There's 3 current transducers. This is just a typical layout of a unit. And a CT, it's a current transducer. It's going to give us feedback to our power board and control board that's going to tell us the current that the motor is running, the torque that's running on that motor, and that's how we figure overloads and over torque and that type of stuff. So again, if you're running and you're seeing overcurrent trips on the drive or overload on the drive, and so you have your clamp on meter, you can go out there and actually check what is the current. And if you have a situation where the drive is saying, well, your motor is pulling 50 amps and you're being overloaded, but your clamp on says, I'm only pulling 32 amps. Yeah, something's awry probably in this circuitry. So your feedback is not equating the same as an independent amp clamp. So it's either CT is bad or that is feeding back to the power board. That could be faulty. This is a typical layout of a IGBT, a power IGBT. And again, they're all different sizes. This is just an example of one that contains two IGBTs and one module. The output, as I said, is a pulse width modulated type output that varies. The width of the pulse varies based on the frequency that you're telling the motor to run. If you had an oscilloscope, you could monitor the output of the drive, and you should see nice, evenly spaced pulses. Typically, if you had a transistor problem or a gating problem or a power board problem, you would be missing what they call the picket fence would be missing. So some parts of this fence would be missing, and you would know that, kind of like a car that's misfiring from spark plugs. You would know that you had a faulty a power board or a faulty gating device. And this goes through what I just kind of went over. Here's the physical placement of the drives. It consists of about 3 different parts. You have your control card, which we talked about earlier, with a keypad on it, and your control IO is all right here. Then you have a power board, which would be all your power supplies for regulating things as your the DC fans to come on and off, power supply for your control board, and so on and so forth. And then your gate driver boards, which obviously is to turn on the IGBTs, and larger drives, it would be used to turn on the SCRs for the front end. So we've gone through the drive, the power section of the drive. We've gone through the termination of the control wires and the power wires. And if everything now is okay, then we're obviously going to have to take a look at the drive and power it up. And I'm not going to be able to go through in this section or in this session here all of the faults and all of the programming that you would encounter if you did have a fault on the drive via the keypad. But I just wanted to share with you the keypad on a VLT. It's pretty intuitive and really informative. This is a fault that I simulated, and it's basically telling you it's the alarm and trip state. So it's a safe stop, and there's the fault number in A68. So you can look in the manual under safe stop or under A68, and you find out everything you want to know about what is safe stop. It's also telling you that the drive is off, it's in local control mode, and you're tripped. You're not in a warning state, you're in an alarm state, you're tripped, you're not running. So as per 99% of the time, you don't have a manual there next to the drive, or the customer doesn't have a manual there next to the drive when he's talking to you and asking and saying that the drive is tripped, and this is what the keypad says. So there's an info key right here to the right-hand side of the keypad. You depress that info key, the manual actually comes up on the keypad, and it gives you a definition of the fault and corrective measures. So it's a safe stop has been activated. To resume normal operation, you will need to apply a 24-volt signal to terminal 37, then send a reset signal. And you can see there's actually more verbiage here. If you press the down arrow, it will scroll down, and that will give you everything that you would see that's going to be in the manual. And this is not only just for faults. This key is active for non-fault issues like parameter descriptions. So if you're looking and the customer says, man, I would like to have a relay output that controls my lube pump over there when it reaches 20 hertz. You can go through here and you can go to your relay output section, and they could be programmed for various number of things. You can start to scroll through and you see a command, and you say, I think this will work for that. You hit the info button, it'll tell you all about that function for that relay, how it's initiated, how to set it up, and how it works. So it's extremely helpful. It's intuitive, and it can actually save sometimes if you have a customer that's calling you, and you can step him through this little process here of just giving you what the alarm is and the info button. You can hopefully step your customer through an issue without further needing to go on site. So let's see, Michael, I think that's about it. That wraps up the basic troubleshooting for the VLT series drives. Thank everyone for listening.
That was fantastic, Chris. You really went into a lot of detail. That's wonderful.
Thank you.
Thank you all so much for attending. At this point, I don't see any questions unless you want to comment, Chris, on, there is one question, and that is, what is the reason for having 3 protective earth conductors within VFD cable?
Let's see here.
And we can certainly get back to this gentleman.
Yeah, I think there's an answer. Looks like John answered. He has a link to a Southwire, and it all depends on the application, is what I can say, and the different types of protection you need. I know there's as many types of shielded cable as there are, anything else. So depending on what exactly your application is and sensitivity is some of the reasons for the different types of shielding and the way they do their internal conductors.
Great. Thank you so much, Chris, and thank you to everybody who participated.